we're going to consider a couple of generalizations of mathematical induction. The first being the case where the basis is something other than 1. And in that case, we might have a statement P of n that is true for all integers greater than or equal to some capital N, but capital N is strictly greater than 1. May not be true for all positive integers, but it is as long as n is as big as capital N and thereafter. So we can use the same strategy, the principle of mathematical induction. It changes the basis step because we'll start with P of n rather than P of 1. And so we'll look at this example where we prove that n squared is less than 2 to the n, at least starting at some point. And let's investigate when that might be. So the table includes values of n squared and 2 to the n, so we have n squared here and 2 to the n here for various values of n. And when n is 1, then it is true that n squared is less than 2 to the n. 1 is less than 2. But at 2 we get equality, not a strict inequality. And at 3 it fails. 9 is not less than 8. At 4 we get equality again, but now at 5, 25 is less than 32. And at 6, 36 is less than 64, and it appears to be getting a greater difference between them. So perhaps it works from 5 and on, and that's what we'll claim. So our claim is that for all integers n greater than or equal to 5, n squared is less than 2 to the n. And as usual, we'll identify the statement, let P of n be the statement that n squared is less than 2 to the n. The basis step this time will be the step when n is equal to 5, in which case we will say the statement is 5 squared is less than 2 to the 5th. And if we calculate that as we did above, that statement is 25 is less than 32. That is indeed true, so P of 5 is true. So that completes our basis step. For the inductive step, we'll let k be an integer such that k is greater than or equal to 5. We have to start it there. That's where it starts to be true. And we'll assume that P of k is true like we normally do, and show then that P of k plus 1 is true, that it will be true for the very next integer. So right now we're assuming that k is greater than or equal to 5 and that k squared is less than 2 to the k. And our objective here is to try to show then that k plus 1 squared is less than 2 to the k plus 1. That's what we're trying to do right here. So in the proof itself, I'm going to say, as we work to obtain P of k plus 1, that thing on scratch above, let's note that k plus 1 squared is k squared plus 2k plus 1. That will be helpful because we can see right here part of what we already know, and then part of what we don't already know. And at the same time, we know that 2 to the k plus 1, the other side up here, is equal to 2 times 2 to the k, and I do it that way because we know something about 2 to the k. That's equal to 2 to the k plus 2 to the k. So if we look at the two sides, and let me just draw your attention to those again. If we look at the two sides, there's the one side, and here's the other side. Then part of it is already in our hand. K squared is less than 2 to the k. So what we'd like to be able to do is say that 2 to the k plus 1 is also less than that other term, 2 to the k. And as I've said in the proof, we would be done if we can show 2 to the k plus 1 is less than 2 to the k. So there's various ways of doing this, and I'll show you one way that we haven't done in class. Let's just note then, but since k squared is less than 2 to the k, it is enough to show that 2 to the k plus 1, that extra chunk that we have here, is less than k squared. So various strategies, as I've said, and one way to do this is to subtract. So we will show 0 is less than k squared minus 2k plus 1. right? That's equivalent to this expression right here. So we'll show that 0 is less than k squared minus 2k plus 1, which is equal to, I think I'm not going to be able to squeeze it in here, maybe I can, k squared minus 2k minus 1, right? I want to show that is positive. Well, let's see. We'll write k squared minus 2k minus 1 is equal to, you know what I'm going to do here is factor out the k of this part here and write that as k times k minus 2 minus 1. Because we can analyze how big that is since we have assumed here that k is bigger than or equal to 5 up above, right? So this is greater than or equal to 5 times 3 minus 1, which is 14, which is definitely bigger than 0. Thus, k squared is bigger than 2k plus 1, meaning that 2k plus 1, that's the thing I wanted to show was less than 2 to the k, is less than k squared, but under our assumption up here, that's less than 2 to the k, so k squared plus 2k plus 1 is less than k squared plus k squared, which is less than 2 to the k plus 2 to the k. And by our understanding of how that works out, this says that hence, let's go ahead and capture it all together, that's k plus 1 squared is less than, and that's 2 times 2 to the k, or 2 to the k plus 1. Okay, so there we can conclude, thus p of k plus 1 is true, and that is p of k implies p of k plus 1 as long as k is greater than or equal to 5. I won't say that right here. And that concludes the inductive step, so therefore by mathematical induction n squared is less than 2 to the n for all integers n greater than or equal to 5. Okay, and again, as I've emphasized, that's the only time we have that for all integers with a certain condition, this time n greater than or equal to 5. Okay, well, the next video we'll do something called strong induction, another variation on induction.